I'm going to be talking about how we use Kubernetes and Nomad at CircleCI, and how we run one inside of the other, and a little bit of why we do that. So let's get started. So who am I? I'm Danny. I live in Berlin, and I'm a staff software engineer on the build execution team at CircleCI. I'm also a maintainer of CocoaPods, a dependency manager for Mac and iOS applications, and Fastlane, which is build and release tooling for mobile engineers. And if any of you haven't heard about CircleCI before, CircleCI is a continuous integration and delivery platform with first-class support for Docker, macOS, and Linux VMs. And so what am I going to cover in this talk? I'm going to start out by covering why we decided to replatform our infrastructure. And I'm then going to talk specifically why we chose to use Nomad and Kubernetes together. Because the first thing I say when people hear this is a bit of a confused look, for good reasons. And then I'm going to talk about how our deployment has evolved, and a few sort of mini postmortems about some fun production outages we had a few months ago, and how we managed to overcome them using Kubernetes. So almost a year ago, we launched the current generation of the CircleCI infrastructure, aptly named 2.0. And it was a huge amount of work that involved everyone inside the company by the time it was released, which might sound a little bit strange when we're a CI and CD company, that we would take a year to go away and build a thing before we shipped it to anybody. But why did we do that? CircleCI was founded in 2011, and this was a very different time for many software companies. Many places were not even starting to do CI and CD yet, and we didn't even have Docker yet. And so many teams deployed AMIs or were running configuration management tools against hosts in production to sort of like git pull and bundle exec rake serve. Hopefully nothing that sad, but we've all been there. The platform was originally designed around being fairly opinionated about how your CI and CD process should work, with explicit sort of demarcations for when you build, you're testing, and you're deploying. And this was great when we were all writing like these huge monolithic Rails apps, with relatively simple deployment pipelines. But in the time since then, however, the industry has changed a lot. Docker was released in 2013, and since then, it's had an incredibly broad impact on how teams are building and releasing software. We could see where our own and where the industry requirements around CI and CD were going, but our existing infrastructure was rapidly becoming a problem, and we couldn't see an incremental path towards servicing them. And so we eventually decided that our best option was to tear everything down and replatform our core infrastructure to allow us to service these ever-changing needs. Replatforming is terrifying. Like, it's a lot of work. You're taking an existing thing that's working reasonably well, and you're trying to rebuild a better version of it. And you have to do all of this work without the constant guiding light of all your customers' feedback. And our customers were also scared, because it looked like we weren't really doing anything for a year. But we had the advantage of existing domain knowledge and understanding of what we needed from that infrastructure. So we had a couple of key requirements to think about when we started down the road to 2.0. We needed to handle both the needs of our build infrastructure and also a way to scale out our platform as we migrated from our old monolithic app to microservices. Running other people's code on your infrastructure and on the same servers as other people's code is a terrifying thought. Like, raise your hands if this is something you would willingly want to do on a daily basis. There's not even a single brave soul out there. That's wonderful. And this is for good reason. And so because of this, we have to bake in strong isolation to everything we build, and we have to do it from the beginning. And security is not something you can just think about after the fact when you're running like arbitrary things on your environment. And there were a few ways we could do isolation in a reasonably safe way, and the one we picked for CircleCI 1.0 was LXC. As you can see, this is a perfect representation of a sandbox, as just everything flaps around everywhere. Over the years, we've become pretty adept at managing the nuances of LXC and its tools. Like, we know what they do, how they work, and we understand a lot of the edge cases. And so we wanted to capitalize on that experience by picking tools that shared many of these qualities. And on 2.0, alongside wanting to support containerized builds, We also had to offer first-class support for alternative environments, such as running on a full Linux VM or macOS VM, for building software that needs more resources, or if you're wanting to build and publish Docker containers, or testing your iPhone app. We also have some slightly interesting scheduling concerns. At our peak, we push thousands of jobs per minute, and many schedulers can't handle large volumes of very short-lived batch jobs. Many job schedulers that are designed for running long-running services or processing large, expensive tasks tend to have fairly slow schedulers that optimize for finding optimal placement rather than trying to schedule it quickly. And these types of scheduling algorithms tend to become quite expensive when you're trying to schedule this many jobs on a very large cluster of machines. And Circle CI isn't just a SaaS product. We also have an on-premise deployment option. This means that any tool we deploy as part of our product needs to be operable by people who are not necessarily domain experts and offer the power to automate away most of the rough edges. And that sometimes means we are more sensitive to manual ops overhead than many other organizations. And at the same time, we were looking for a platform that would enable us to run our product, services, and infrastructure, that would allow us to scale out beyond the single development instance that was the first prototype of 2.0, and support us for the considerable future. And so this is going to sound a little weird to everyone at a Kubernetes conference, but our initial search landed us with two options, Mesos and Nomad. Mesos had the advantage of being extremely robust and battle-tested, operating at ridiculous scale in places like Twitter, Airbnb, and Apple. However, a big part of its ability to support those organizations rests on significant overhead for the operator. To use Mesos, you also need an orchestration framework like Marathon or Kronos, and depending on the one you choose, you get a very different experience. And for our build infrastructure, we needed good support for batch jobs, and Mesos didn't have a great solution for this. And it's a good tool, but it was definitely not the right tool for us with the engineering capacity we had at the time. And we'd have had to write a lot of code to make it do the right thing. And we already use a bunch of the HashiCorp stack, provisioning our infrastructure with Terraform, and building our AMIs with Packer. So HashiCorp's still very young Nomad was an interesting contender. And unlike many orchestrators, Nomad can choose between a few different scheduling algorithms. And for batch jobs, uses an algorithm based on the Berkeley Sparrow scheduler that applies a power of two choices load balancing technique to job scheduling. And this results in a job scheduler that is incredibly fast. Nomad's executor is also incredibly pluggable, with built-in support for running various container technologies, or simply allowing us to execute an arbitrary binary, allowing us to precisely control how we set up and execute our customer jobs. This is incredibly useful for us as we start supporting things like virtual machines, or supporting running multiple services alongside your primary build container. It also has an incredibly powerful API that exposes most of its state, which is really great for when we're building out our scheduling capabilities, and when we want to provide tools on top of Nomad to automate its use in our on-premise deployments. Nomad was also still very young, and we could talk with the Nomad team and influence its direction, and contribute our own patches upstream as necessary with relative ease. It's also still rapidly evolving, with many ops changes coming that allow us to remove many of our own out-of-band patches and sidecar tooling that I'll talk about later. That being said, this usefulness came with some problems, whereby there were various stability and operational issues that would force us to SSH in and restart random processes because things would be wedged, or somewhat randomly failing. And so, because of our desire for strong isolation between builds and internal services, we came to an interesting realization. We didn't need to use the same tool for both our job execution and our internal infrastructure. This would allow us to leverage the tools that make sense for the problem domain, without trying to shoehorn the capabilities of one into the other, or maintaining huge amounts of code to emulate the features we wanted. And we definitely still didn't want to operationalize Nomad, and eventually we decided on using Nomad and Kubernetes together. Unlike many of the other orchestration options at the time, Kubernetes was already approaching the point of being relatively stable, and used in a growing number of large-scale production environments, and has, like, as you can see here today, an amazing community of people around it. We also had members of our SRE team that had used it in previous jobs. And the lifespan and adoption of the tool gave us confidence that others had encountered similar problems to us, and perhaps knew how to solve them. Being able to go to an IRC channel or a mailing list or Twitter and have people have potential ideas about how to solve the problem is really valuable. So as I was saying, a big part of we didn't want to use Mesos was that a lot of its operational knowledge is locked in the silos of very, very large enterprises. And nobody on our team already knew how to use it, and filling in those gaps without the community would have been an impossible mountain. And so that's really one of the main factors that gave us the confidence we needed to push to use Kubernetes in production. One of my other favorite reasons of using Kubernetes in our specific workload was the great support it has for doing rolling updates and readiness checking. We continuously deliver all of our software. And regardless of how much you test a service, knowing that if you push a bad config change, your service will crash and not be rolled out to all of production, thus taking everything down, it's just like a warm hug from your computer. Usually, they just make me want to throw them into the sea. And in the case of running a stateful service like Nomad, it allows you to maintain quorum during deployments, which was one of the more frustrating issues during our testing phases. Kubernetes also strikes a nice balance of giving you a lot of valuable functionality with reasonable defaults somewhat out of the box, while allowing you to replace most of the components without having to reinvent your entire architecture, which is really nice when you're spinning up a new piece of infrastructure that you want to last you a while. And so we ultimately made the distinction that Nomad is part of our product, it's where we run builds, and it ships as part of our on-premise product as well as in our SaaS offering. But Kubernetes is what we use for scaling our platform and operationalizing our product. We leverage its features to allow us to run our application layer services and to provide abstraction and automation over our other cloud resources. And so what I'm really saying is it's just schedulers all the way down. Because yes, we do run a scheduler inside a scheduler, and there's even a meta scheduler running inside a scheduler that schedules on the other scheduler. And so now we know some of the tools we're working with. Let's look at a bit of how we set this up and explore some of the things that didn't necessarily go so well, and how we leverage those tools to fix them. And so this was supposed to be a GIF, but apparently it is not a GIF. It's fine. From an operations perspective, Nomad is comprised of two main components: the Nomad server, which is the Nomad control plane, and Nomad clients, which execute the jobs provided by the Nomad server. We run the Nomad servers inside Kubernetes, and the clients are external. And for us, a Nomad deployment also has some auxiliary services that exist to integrate Nomad with the rest of our domain, some monitoring, and a bunch of ops automation. I'll talk more about this in a minute. So Nomad is an inherently stateful service built on top of RAF for handling log replication, and with a couple of different persistence options. Nomad also requires some form of service discovery for initial cluster bootstrapping, after which standard gossip protocol takes over. So how do we manage that persistence? We handled Nomad storage by having dedicated Kubernetes clients for Nomad server workloads, which we then mount the host storage of into the Nomad server container, which allows us to leverage our existing practices for managing stateful services and simplifies our Kubernetes configuration. But this was before many of the new sort of Nomad, the Kubernetes storage APIs really existed. And because Nomad is a distributed stateful service, it also requires some way to do discovery of other server nodes. And there are a few ways you can do that. HashiCorp recommend using Consul for this. And it works reasonably well with relatively low overhead to get set up and configured. And it's a very stable piece of software. However, our initial Consul setup was a little bit of a snowflake cluster, and it was not running within Kubernetes. And so when we started expanding our Nomad requirements to deploy multiple clusters, we found we were initially using the same Consul cluster for multiple deployments of Nomad, which when it comes to minimizing shared dependencies and isolating clusters was not an ideal solution. So we started evaluating alternatives before trying to deploy yet another stateful service inside Kubernetes. And we eventually decided on switching Nomad into using a Kubernetes stateful set, which gave us really predictable upgrade semantics when wanting to maintain quorum, and also allowed us to do our initial Nomad server bootstrapping using only Kubernetes for service discovery. And I'll talk a little bit more about how that works later. Nomad clients are where jobs actually execute, and these don't run inside Kubernetes, but instead within a standard AWS autoscaling group. We scale the clients with a fairly simple autoscaler that is driven by our metrics and goes through an alerting pipeline, which then goes through RabbitMQ, which then gets scaled. It's a wonderful internet Rube Goldberg machine. But it comes with the added side effect of it's really easy to shut down or override when we want to over-provision for expected spikes and other such changes, or when migrating over to a new cluster. We originally used a patched version of Nomad to support draining clients without rescheduling jobs on other nodes, and a Nomad draining service that consumes the AWS lifecycle hooks to enable and disable draining as required. But a newer version of Nomad that was released last week adds first-class support for controlling the drain behavior of clients. And as we start our testing and upgrades, it should be fairly simple to update our drainer to use the new API for this. We also run an agent on Nomad clients that validates that Nomad is up, the status of the Docker engine, and the internet reachability. This then reports to CloudWatch and StatsD and all the things, so we can automatically drain and remove unhealthy nodes without intervention. A few months ago, we also migrated to running inside multiple clusters, as I was saying, to provide redundancy and also to make it easier to canary new releases of Nomad and our surrounding tooling without affecting all of our customers' workloads. We leverage some really nice Kubernetes and Terraform features for this. We deploy all of our infrastructure using Terraform because it gives great visibility into changes onto our deployment and allows us to easily reason about and change our configuration. One of the first steps in migrating to a multi-cluster deployment was to modularize our Terraform to allow us to easily create multiple downstream clusters with minimal duplication. We then migrated all of our Kubernetes manifests for our deployment into Helm. We actually packaged the entire deployment alongside a bunch of sidecar services that provide garbage collection, draining, metrics, and other services into a single Helm package. This makes it really easy for us to be able to both use our standard CD pipeline to upgrade Nomad, while also being able to really easily manually deploy a cluster if CircleCI is down, which is really useful when you deploy all of your things using production. It's the wonderful thing about working on CI, because you use CI to deploy the CI. We then deploy each cluster into its own namespace in Kubernetes, which acts as a neat grouping mechanism for all of the related services and allows us to easily manage an individual cluster, and acts as a good isolation boundary for services that want to talk to a deployment. The use of Kubernetes namespaces alongside a stateful set makes it easier to both handle auxiliary services to discover their related Nomad deployment, and also for Nomad servers to discover each other, as they have deterministic DNS names provided by the stateful set that we can then use in the Helm template to make it know where to look. But as with all things computers, though, it has not been entirely a magical land of rainbows, unicorns, and sparkles. We've definitely experienced some rough edges of both Nomad and Kubernetes, such as when we were trying to fake taints and tolerations in old versions of Kubernetes, and also some rough edges of Nomad. That being said, we've been able to overcome and work around them. And in the latter case, Kubernetes has been super valuable in that. So it's time to talk about some outages. The first major set of production outages we experienced with Nomad were in January, and taught us a lot about some less obvious behavior in Nomad, and resulted in some changes to how we deploy our clusters to Kubernetes, and how Nomad does some things. So the symptoms were quite interesting. We initially got paged for the Nomad job queue starting to rise quickly, despite us having significant capacity to be able to run users' jobs. And all of the Nomad clients and servers appeared to be up and healthy and working normally by all of their metrics. And so after digging into this for about half an hour, we were getting very confused. Because we were definitely nowhere near our peak load, But as we looked deeper, we saw that nodes were simply not receiving jobs anymore. And so we started to take a look into the Nomad servers and saw that almost all of their logging had stopped, outside of a significant number of failed to delete job requests. In an attempt to unwedge the hosts, we started just like cycling the Nomad server pods, which allowed some amount of jobs to pass through. And ultimately, in this case, we ended up making the tough call and just dropping our Nomad state completely and rebringing up the cluster from scratch. And in follow-up from that, we were reanalyzing our configuration and source code and the source code of Nomad, and we noticed we were missing some options that would give us greater visibility into the operations of its internal state machine. So we quickly enabled them so we could get more data the next time this incident occurred. And with all things computers, it turned out we wouldn't have to wait so long. The next day, we were once again greeted by the same lovely page. But this time, we had the metrics we needed to identify the issue. We were quick to declare bankruptcy after validating we had the data we needed and doing some manual introspection of the running state. And so when analyzing the data we'd collected, we eventually realized the issue was occurring during garbage collection cycles, where Nomad will cycle through all of the completed jobs and try and remove them from its RAF database. The original implementation of garbage collection in Nomad would iterate over every job that needed to be collected and issued a separate request to the cleanup engine, which would take a slot in the RAF transaction log, which would then need to be applied to its state machine. And each of these requests would then call out to the current Nomad leader and block until the deletion had been applied, which was not ideal when you had several 100,000 jobs trying to be deregistered at once. And when multiple nodes may be issuing the same GC command at once. And so we initially tried reducing the GC cooldown from the default 4 hours down to about 30 minutes, under the guise of, if you're doing it more often, you have less stuff to clean up. Which resulted in much more stable behavior. However, it wasn't quite perfect, and around our peak times, scheduling would halt for just like 10 seconds while it was going clearing up some state, which was just slow enough to trip our pending jobs alerts. And so, because we only really use the Nomad API to introspect jobs that have failed, we don't really need to keep around jobs that are in a successful terminal state. So we wrote a small service that uses the Nomad API to continuously collect dead jobs. And we use the built-in collector as a failsafe in case that our service is unavailable or cannot reach the Nomad API. This resulted in significantly more stable operation and was significantly easier to deploy through our usage of Kubernetes because we added it to our Helm package, pushed, and then we had garbage collection. The latest version of Nomad now actually batches deletion requests, which should see much better performance in this type of usage environment, and should allow us to archive our own garbage collector. It also introduces a new API for draining nodes and controlling the way that jobs would migrate to a new instance, which should allow us to delete our fork, which I'm pretty excited about. It's super exciting to see these types of changes coming to Nomad as part of their autopilot feature set, and I'm excited for its future. So in summary, Kubernetes, Helm, and Terraform have made it significantly easier to orchestrate our build system. And I'm personally really happy with the power and control that they've given us over that, and the ways they've given us to handle our clusters. And also with Nomad, which is continually improving and becoming easier to operate, while still being incredibly fast at scheduling our customers' workloads. And so I'm happy to take questions if there's time or if that's a thing, but everyone is more than welcome to come chat with me if you see me around the rest of the conference. Thank you.